Hi all, and thanks for joining this webinar. My name is Christoph Hahn, and with me is Yatin Anand. Today we will share with you insights into testing and certification for more electric aircraft and full electric vertical takeoff and landing aircraft. Let's get started. The aerospace market is growing at a fast pace, and new concepts are emerging continuously. One megatrend certainly is the rise of electrified powertrains, and development organizations are looking into energy storage and more efficient processes all along. Another megatrend, of course, is the increasing connectivity between aircraft features and among aircraft, leading to more complex integration tasks such as power conversion. The growth of the air mobility market is strongly coupled to increasing sustainability. So, to become a commercial product, new technologies need to be certified. New, faster and more reliable methods for testing and certification are needed due to the increasing number of requirements. In today's webinar, we are going to look into electric and more electric aircraft. The shift towards electric aircraft is crucial for reducing environmental impact and meeting increasing regulatory requirements for sustainable aviation. There are three main focus areas. First, electric powertrains enable new use cases. For example, for vertical takeoff and landing airplane. Battery management systems, so robust battery control is essential for the safety of the aircraft. Also, control systems. For all kinds of actuators and connections need to be reliable. Despite all these new trends, all systems involved need to be reliable and safe under all operational conditions. They need to meet the stringent requirements of aerospace authorities, and all systems need to interoperate well. In the following, I would like to show you how engineers can successfully handle all those complex tasks using an end-to-end development and testing solution by MathWorks and Speedgoat. You will learn how to benefit from a fully Simulink integrated solution that provides flexible and automated workflows. Powerful digital twin simulation software, hardware emulation solutions, and Modular X for hardware in the loop testing, or hill testing in short, that can scale with your needs. Before we dive deeper into these solutions, let's review today's webinar agenda. First, I'll introduce typical workflows and the key capabilities of the solution. Then we'll shift the focus towards dedicated controller hardware-in-the-loop testing solutions covering eVTOL powertrains and more electric aircraft with two hands-on demos leveraging Simulink and Speedgoat Test Systems. So let's get started. What we see here is a default model-based design control development workflow. Every development project starts by defining the requirements. Also in aerospace development, compliance to requirements is the overarching goal. Depending on the requirements, they are either stored in documents or tables. Others may already be put into more structured environments like doors or other tools. Some requirements may even change along the way, but that will pose no problem if those requirements are rigorously tracked and connected to tests. Let's see how requirements and tests are connected. Well, engineers add those requirements to Simulink and convert them into test cases attached to certain models. This enables verifying that new designs meet the requirements. Already here, it becomes obvious that a single location for all test cases is utterly beneficial. So Simulink is not only the development and testing platform, it also helps tremendously to trace requirements. Let's look a bit deeper into the details. So you can import requirements from various sources, and the standard requirement interchange format is supported. You can also author requirements directly from within Simulink. With the requirements stored in the development environment, it is very easy to create links between requirements, architecture, design, test and implementation code. Links can be inserted in other tools for traceability, from these tools to MATLAB and Simulink. The coverage analysis reveals the gaps in the implementation and testing. No problem if requirements change, because if there's an update, there can be an update operation that synchronizes the changes and notification is given on what is impacted by the requirement change. Reports can be generated for documentation and reviews that include traceability. Now, I would like to show you how model-based development fits into your aircraft system development according to Aerospace Recommended Practice, or ARP in short, 4754A. ARP 4754A is endorsed by civil aviation authorities to provide best practices for demonstrating compliance with regulations. The development process is broken down in several stages: functional development, allocation of functions to systems, system architecture, requirement allocation, and system implementation, ending with documentation. To have a complete development and certification, it is important to have a tool chain covering the entire process. So if you are using Speedgoat real-time test systems, you will have a unique and complete integration into MATLAB and Simulink from MathWorks. So all in all, real-time testing enables compliance with ARP 4754, as all aspects of this guideline are covered. We have seen this development workflow with its stages before. So after requirement definition, you may want to evaluate some early designs on the desktop. You will likely run some promising control designs on powerful prototype controllers to test how they behave when controlling the actual plant. Once your controller is available and you've successfully implemented your design, you can test your controller as hardware in the loop. So let's dive deeper into these two concepts, starting with controls prototyping. In rapid control prototyping, the plant could be your aircraft or Ironbird. The development task focuses on the design of the controller. This means that the real-time target machine emulates the controller and executes the code of your embedded control design in deterministic real time. Performing control tasks in a loop allows you to verify that the controller fully meets the requirements. Early testing of a control algorithm can help you to eliminate errors early on. Once you are happy with your control design and its behavior in the prototyping setup, you can automatically generate the algorithm in C or HDL code. After compiling the code on your controller, you can then go ahead and test it. You probably do not want to directly put the flight controller into the aircraft. Therefore, you can conduct hardware-in-the-loop testing, where you take your physical controller and run it against a real-time test system, which is a physical representation, or one could also say digital twin of your plant. I would like to emphasize the key differences between testing based on data or based on data acquisition and hardware-in-the-loop testing. Most of you are already familiar with some form of data-driven testing. Engineers use this in their everyday life, record data, do some post-processing, and for open-loop testing. A key advantage of hardware-in-the-loop testing is, and the expression already has the keyword in it, closed-loop testing. This means that you can run dynamic scenarios and interact with your controller. The complete test process can be automated, allowing you to perform complex tasks with a click of a button and to automatically generate test evidence using automated report generation at the end. You can test against a set of requirements and perform regression testing in case you have some last-minute changes to your code. This approach allows you to test your controller in real time, which cannot be achieved by just doing measurements or data acquisition. Beyond that, hardware-in-the-loop testing allows you to perform system-level integration testing under all possible operational conditions. Electrical vertical takeoff and landing aircraft, or eVTOLs in short, as well as conventional airplanes, consist of many subsystems. These subsystems must be integrated into one system. To integrate all these subsystems and components, system integration labs, or Ironbirds, sometimes called eBirds if the aircraft is purely electric, have become industry standard. All relevant systems and connections are integrated in this lab setting to have an accurate representation of the aircraft. This can be purely on a control level, depicted in blue color on the screen, but it can also contain power systems and representations of the powertrain, including high voltage components such as inverters. This is indicated in orange here. To get an accurate representation of different flight states, the complete system needs to be run in real time with the respective sensor feedbacks and flight states. Therefore, the digital twin needs a host system which allows to interact with the Ironbird. If individual components are emulated instead of being integrated into the Iron Bird, the real-time hardware-in-the-loop test system can handle this by emulating necessary signals, voltage levels, and mimicking the subsystem behaviors. To test software according to the DO178C standard or hardware to the DO254 standard, it's crucial to ensure all controllers operate as if they were in an actual aircraft and flight state. Therefore, the same twisted pair wiring and voltage levels, such as 28 volt for avionics, are used. This setup allows engineers from approved design organizations to automatically test the required failure cases and provide data to the certifying authority. So both EASA and the FAA not only accept but also encourage the use of laboratory simulation as a means of demonstrating compliance. Let me give you a better overview on how a hardware-in-the-loop test system of an e-bird is composed and used. There are typically three main components in a Hill test system. First, your system under test. This includes the production controller that requires thorough testing and additional physical components like domain controllers, sensors, and actuators. Second, a Hill test bench, including a real-time simulator where you can run a digital twin of the plant together with emulated plant components and I/O modules supporting data acquisition, signal condition, and communication with the system under test. Third, a workstation running application software that supports the setup and operation of the Hill test bench. Speedgoat's performance machine is the most scalable and performant system with highest I/O flexibility. It is the mainstay for hardware-in-the-loop testing, or Hill testing in short. The mobile baseline and unit machines are smaller and rugged, making them fit in applications requiring more portability and fewer I/O channels, like rapid control prototyping. The performance test system is suited for desktop use, but also for rack mounting. Speedgoat's Hill system team can provide you with fully customized rack systems for Hill testing, including easy access to all signals via breakout and I/O panels. We'll integrate power supplies, actuators, inverters, and any kind of power electronics, as well as project-specific PCBs for signal routing and conditioning. Let's move on to focus on dedicated solutions for controller Hill testing of aircraft controllers. We'll start with a workflow demo for an eVTOL powertrain. Yatin, I'm handing over to you.
Thanks, Christoph. In this demo, I will be focusing on ECU Hill testing of eVTOL powertrains. I'll start by exploring the hardware setup and the eVTOL digital twin model behind this demo. Then I'll move on to the actual Hill demo and cover eVTOL real-time simulation, unit-level testing of battery management system and motor control units, and finalize by showing how to automate testing of requirements for specific system-level test cases. So let's start by outlining the Hill test system setup. We are using a smaller scale demo test setup to test two powertrains controllers, a motor controller unit that governs operation of one of the two 200 kilowatts electric drive, and a battery management system composed of a battery management controller unit that is connected to two real cell monitoring units. ECU communication runs over a CAN network. For the eVTOL digital twin Hill simulation, we are using a performance real-time target machine. This system runs virtual ECU simulations for the flight controller and remaining motor control units. The eVTOL Dynamics FPGA-based motor drives simulations that enable encoder and current sensing emulation to real motor control unit, as well as a 400 volt battery simulation model to meet the interface needs of the two real cell monitoring unit and enabling testing of analog front end. We have integrated two battery cell units, providing realistic cell level emulation for 24 out of the 100 cell of our battery pack. As this demo system does not integrate emulation of hardware for temperature sensors, the current shunt, or the missing cell monitoring units, the simulated signals are fed to the BMS controller through existing CAN interface. The entire Hill test system is managed from a host computer, which enables control and monitoring of real-time application as well as a 3D visualization of aircraft and surrounding scenes. Let's now switch to Simulink and check how these blocks map to a real-time application and Simulink models. Our eVTOL model features a flight controller that sends commands to the motor drive, which integrates 4 rotary propulsors. The battery system consists of a 400-volt battery and a battery management system that ensures safe operations and cell balancing. The flight dynamics subsystem adds physics and gravity, enabling us to visualize vertical takeoff and landing aircraft in Unreal Engine while flying a mission within an urban environment. Let's leverage the custom active workflow of UAV toolbox to visualize aircraft performance in a photorealistic environment. Different simulation modes can be selected for BMS testing and motor control tests. The options include hardware-in-the-loop testing, which allows us to emulate the battery on a battery cell emulator and test battery control algorithms on an external ECU, and a real-time motor simulation on a Simulink programmable FPGA, enabling the simulation of high switching dynamics, fault insertion, as well as encoder and phase current emulation, while testing the motor control algorithm on an external ECU. We can also select desktop simulation, which allows us testing in the initial development phase, which is useful for iterative debugging sessions. The model also serves as a digital thread connecting design requirements to model components and test cases using Requirement Toolbox. Requirement Toolbox enables us to validate requirements within MATLAB and Simulink. The requirements are linked to a subsystem where it's implemented. For example, the logic for battery voltage drop limit is implemented in the BMS controller subsystem, and the calculation of state of charge is verified using a Simulink test linked to a Simulink test manager, as you can see here. Simulink test manager is a tool that helps to create test cases for Simulink models and code in Hill execution environment. This allows us to formalize the requirements and analyze them for consistency, completeness, and correctness using the requirements table. Let us start the demo by running our eVTOL in real time for a guidance test. The system user interface displays motor speeds for all 4 motors, battery voltage, current, power, and the state of charge of the battery. It also displays the currents from the motor for system level monitoring and testing. We can also manually control the aircraft to handle specific maneuvers by changing the input commands to the aircraft. As the guidance test scenario runs, the rotary wings move the aircraft from its initial position to a certain altitude, hovers, makes some turns, and eventually lands back vertically. We can observe the maneuvers in a 2D visualization along with the path taken by the aircraft as well. We also see the battery voltage dropping as high currents are being discharged. Let's now zoom in and examine our battery and motor drive system, focusing on unit level hill testing for battery management system and motor control units. Our 400-volt battery is modeled using Simscape battery. It consists of 100 cells grouped into 3 modules of 24 and 38 cells. One of the modules of 24 cells is emulated on two battery cell emulators, 12 cells in each emulator, and the other cells are simulated in this reference example. Essentially, we can emulate up to 252 cells by daisy chaining multiple battery cell emulators depending on your use case. The 3 modules are connected to a fault insertion interface, allowing fault insertion at the cell level, and a passive balancing interface to effectively mimic the cell balancing currents issued by the BMS controller. As mentioned before, the first module containing 24 cells is connected to two Speedgoat battery cell emulators. This enables cell level emulation and provides a hill system with an analog interface with the 2 cell monitoring units of the battery management system. The interface with battery cell emulators can be done with a few clicks using a dedicated hardware configuration user interface. To test the BMS, we can select Hardware in the Loop Simulation mode. This adopts the hardware interface to work with the actual BMS controller. For instance, here we can see the CAN interface which transmits battery data such as the cell temperatures and pack currents. At the same time, it receives signals from BMS controller such as current limits of fault, charge and discharge, state of charge, and fault diagnosis data. Let's build and run the configuration to start hill testing of BMS. BMS user interface also helps us monitoring of important parameters in the battery system like the battery voltage, current, state of charge, and power. It also allows us to insert faults and observe all cell data by just entering the cell number. You can observe that the state of charge, voltage, temperature, and current for each cell that you enter. For instance, we can validate the BMS cell balancing. To do this, let's override the voltage of cell number 1 to 1.5 volts. You can observe that the voltage for cell number 1 is now 1.5 volts. We can see that this effectively triggers cell balancing on the other cells with discharging currents occurring at a much higher rate to match the state of charge of cell number 1. For example, it can be observed that the cell number 10 has a balancing current of about 78 milliampere. We can also use this UI to introduce faults. For instance, I will add a short circuit fault to cell 10. We can observe that the voltage for cell 10 has changed and is incorrect. Similarly, I will also add a broken wire fault for the same cell. Here the voltage has gone down to 0. Overriding the parameters is also a simple task. Using this UI, you can now notice that the temperature for cell 10 has been overridden to 25 degrees Celsius. As you can see that the cell balancing has stopped after I reset all the overwritten values. Let's now explore the motor drive system. It consists of 4 rotary wings, propulsors modeled using 4 permanent magnetic synchronous electric motors and their respective inverters. Here's a quick look at the motor drive that consists of switching inverters driven by PWM fire pulses captured at 5 nanoseconds, a permanent magnet synchronous motor, and a quadrature encoder that senses motor positions and speed. There is also a resolver, and you can choose to use a resolver or a quadrature encoder. This model runs on a Simulink programmable FPGA at 200 nanoseconds, enabling the simulation of high switching dynamics, fault insertion, as well as encoder and phase current emulation. This allows thorough testing of motor control units ECU at the signal level. All 4 motor drives are controlled by field-oriented control algorithm. These controls can be virtualized to run the eVTOL digital twin and deployed on the intended embedded hardware and interface via CAN bus, which is the option we will use here for demonstrating our motor control unit hill testing. Similar to BMS, we can test the motor control unit using a dedicated user interface. For instance, we can add an inverter fault and also tune the controller parameters live and perform rapid assessment of controller performance. Testing from Simulink with click-based approach is great, but to thoroughly test your controllers, you need to run large set of tests in an automated fashion and have a formal process to validate your requirements. So in this part of the demo, I would also like to show you how you can automate your testing and bring things to system level testing where the BMS motor control unit and the virtual flight controller can be tested together. I've authored a set of requirements-based tests and Simulink tests. In this example, we have system level test as well as unit level test for both BMS and motor control units. Let us run a system test that is linked to one of the requirements and observe the results. The requirements are also linked to a subsystem where they are implemented in this model. Here you can observe all the signals and parameters from your system and validate them. For example, the motor speed and the speed feedback can be compared very easily. Automation is also possible with script using MATLAB API. For instance, I have created a routine that runs the full batch of tests and generates a test report which can be used to communicate results with the stakeholders. This is how you can use Speedgoat and MathWorks Hill testing solution to perform interactive and automated test validation of eVTOL powertrains from components to system level testing. This was the end of first demo. Let's move on to our next demo for more electric aircraft. Let's get started with the Hill test demo for more electric aircraft. The Hill system is composed of a performance test real-time target machine with multi-core processors that will simulate more electric aircraft's digital twin. The system also features an intelligent AirLink 429 I/O module enabling communication with EMS controller. Since I don't have an actual controller available, I will simulate both the electric aircraft and EMS controller components in a Speedgoat target machine and extend my model with the AirLink 429 interface. This lets me validate the controller logic and protocol trivialities in real time. The Hill system is controlled and monitored from a development computer. Let me take you through the Simulink model. This is an aircraft emergency power system with fuel cell, lithium-ion battery and ultracapacitor. The goal of this model is to emulate the scenario of an emergency landing with a generator failure. Let's have a look at how the emergency power system is modeled. On the left side, we see a power generation and energy storage system composed by a fuel cell battery system and a supercapacitor. Let's open the fuel cell block, which is currently configured to simulate a 10 kilowatt proton exchange memory and a fuel cell power module. But you can fully customize your fuel cell stack, check its power envelope, load different predefined cell stack presets as well as customize new ones. The battery is configured to operate as a 48-volt lithium battery system, but you can choose among different battery technologies and customize key battery parameters. The emergency power system is completed by a supercapacitor, 15 kilowatt protecting resistor that avoids overcharging of supercapacitor and the battery, various DC-DC converters handling power conversions for the charging and discharging of energy storage system, and the three-phase AC load that emulates an emergency load profile. Model uses a mix of Simulink and Simscape blocks covering multi-domain and multi-rate simulations of the aircraft power system. That's the plant side of the model. Going up one level, we find the EMS controller. You can see the model supports various controller simulation modes from model in the loop to hardware in the loop, where one can interface with an external EMS controller. I'll go ahead and select the real-time that integrates the AirLink loopback interface as previously described. The signals are sent out from a plant into the controller and afterwards backwards from the controller into the plant. In this AirLink send block, you can see how the protocol is constructed. We send the parameters which come out of the model and we encode them according to the AirLink standard. The standard allows for several communication level settings which can be set in these parameters. Here, the same application may also run a CAN or a different protocol such as AirLink 825, AirLink 664 or MIL standard 1553 for example. Now let's perform a real-time demo and check how the EMS controller and the fuel cell hybrid emergency power system react during a 5-minute emergency landing scenario. I'll select the model to run on the Speedgoat target machine and open a dedicated Simulink user interface for live testing. The overall load is red. Right now it's 0. The fuel cell provides some power to charge the battery, and therefore purple line is negative. After a short while, we will see that the generator is lost. You can immediately see that the load spikes and so does the ultracapacitor. Since the ultracapacitor is the fastest element, it reacts first. Then the outlet of the capacitor is reduced due to the voltage drop, and the battery will react to compensate the voltage drop, and the main load is taken by the fuel cell. The battery is stable at a maximum outlet, which when the load keeps increasing, and even bigger than the fuel cell and the battery capacity. The ultracapacitor will provide the extra power when load drops sharply. The ultracapacitor takes up the transient behavior by actually being charged, while the battery stays constant for a short while. Now with the load further dropping, the fuel cell can provide enough energy to charge the battery again. With the small load, you can see that the plane has landed while it is on the ground. The fuel cell is used to charge the battery. Below you can see some elements like state of health of the battery in case you want to inject different behaviors. You can also override the load manually during the simulation here. This allows for maximum testing flexibility even during ongoing tests. This is the end of the simulation. A potential next step, which I'm not going to show here, is to perform automated and regression tests of your EMS controller. We hope this illustrates nicely how Speedgoat and MathWorks Hill testing solution can support you in expediting development of more electric aircrafts. Thank you for watching. I will now pass the control to Christoph for final takeaways.
Thank you, Yatin. So let's wrap up today's webinar. There's a single key takeaway for you today. Speedgoat Test Systems and the Simulink platform provide a testing solution for all aspects of eVTOL in more electric aircraft development and testing. Why is that? Well, first, you can create digital twins of your systems or its components covering multiple domains running at desired frequencies, such as the switching frequencies of your power electronics hardware. You can develop and test in a single, fully integrated environment that fosters agile development and automated testing. And last but not least, Speedgoat Test Systems are performant, configured to your needs, and provide all levels of emulation capabilities for testing your controllers. Thank you for staying with us until the end of this webinar. You want to learn more about real-time controls testing? Then find additional content linked here.